Language models can write flawless code in seconds and synthesize human history in a single prompt, but ask a machine to turn a standard doorknob, and it will likely freeze, drop its payload, or crush the handle. Digital tasks operate in clean, rule-bound environments. The math is isolated. But walking down a rocky, uneven path introduces millions of chaotic, interacting variables, like the precise friction of a boot on a wet stone, processed in real time. We have built robots for decades, but they rely on strict, hard-coded instructions. A robotic arm on an assembly line successfully welds a car door 1,000 times a day because the environment is engineered to be predictable. Move that car door 1 inch, and the entire system fails. Physical AI is the bridge technology designed to solve this limitation. It combines large, generalized AI models with physical sensors and actuators, giving machines the ability to perceive, reason, and act within unpredictable environments. Giving artificial intelligence a body and teaching it to navigate the chaos of the real world is the final hurdle required for this technology to meaningfully interact with our daily reality. Moving from software to the physical world means colliding with 4 distinct bottlenecks. This chart illustrates our first barrier: expensive data. Training digital models relies on scraping billions of text files almost instantly, but training a physical robot requires real-world telemetry and human demonstrations. Every single data point requires a machine or human to physically move in continuous time, making data collection incredibly slow and costly. The second barrier is the physical world itself. Gravity, friction, torque, and wind resistance constantly interfere. A software model that functions perfectly in a vacuum will break the moment it has to account for the weight of a glass bottle or the slipperiness of a wet floor. Third is latency. Software can afford to take 3 seconds to generate a response. Physical operations cannot. A split-second delay between perception and action causes a drone to crash or a robotic grip to slip. Finally, we face real stakes. A hallucination in a digital chatbot is a minor inconvenience. An error by an autonomous vehicle navigating a crowded crosswalk carries catastrophic, real-world danger. Until these 4 interconnected barriers are broken simultaneously, artificial intelligence remains trapped behind a computer screen. The breakthrough involves creating a digital twin, a hyper-realistic, mathematically precise virtual replica of a real-world environment. Inside this simulation, autonomous machines can crash, drop heavy loads, and break their own hardware millions of times without any real-world consequences, completely neutralizing the danger of physical stakes. Through reinforcement learning, these physical agents run endless trial and error attempts. They learn on their own how to balance, grasp, and move against simulated physical constraints. This visualization shows how the digital twin bypasses the data bottleneck. A single recorded physical scenario instantly multiplies into thousands of synthetic variations. The system alters the lighting, adjusts the weather, and introduces random obstacles, generating decades of training data in hours. Once the model successfully masters these variables in the virtual sandbox, that fully trained, physics-aware brain is migrated directly into the hardware of a physical machine. Advanced simulation acts as a massive mathematical shortcut. It provides the only viable method to safely teach machines the unforgiving laws of physics. Machines equipped with this training no longer follow rigid, pre-programmed scripts. They use generalized reasoning to assess their environments and adapt to new situations on the fly. This intelligence extends far beyond humanoid robots. It coordinates fleets of autonomous vehicles, smart energy grids, and surgical instruments, allowing them to perceive and react to the physical world in continuous time. As these capabilities scale, we're seeing the rise of a new industrial infrastructure. Companies like Scale AI are building robotics data factories, global networks dedicated to harvesting and annotating thousands of hours of human physical demonstrations every day to fuel these models. This surge in data and simulation power is leading to an economic forecast for physical automation. NVIDIA CEO Jensen Huang predicts that this wave of physical AI will eventually lead to a global economy populated by 1 billion autonomous robots. This shift represents the transition of artificial intelligence from digital symbols to the realm of atoms.
If these predictions are accurate, this move will bring autonomous systems out of specialized facilities and into every sector of the global economy.